All right, everybody. So we are going to be doing the last section of Business Cal today. So we are going to finish up chapter 3 by doing section 3.9, which is related rates. This is just a continuation of the implicit section we did in the last video. So not too many problems today, but let's knock this out as your last section. So remember from the last video in section 3.8 that when we take a derivative implicitly with respect to x, we had to add a dy dx term onto each of the y functions. So remember, we did like the derivative of y squared would be 2y times dy dx. The difference today, and I kind of preluded this in the last video, is that we're going to be taking derivatives implicitly with respect to different variables. Since we're going to be doing word problems, we're going to be taking derivatives with respect to time. So what that means for us is some extra terms that we're going to pick up. For example, if you have to take the derivative with respect to t of x squared plus y squared, you'll notice that when you take the derivative of your x squared term to get 2x, we have to also add a dx dt term onto that, along with when you take the derivative of y squared, you add on a dy dt. So that means every single derivative that you take today in these word problems, you will have to add an implicit term onto the end of it. So let's work some examples using this idea before we get into the word problems. So number one, given that y is equal to x minus x to the fourth, find dx dt when x is 2 and dy dt is -5. Well, as far as implicit goes, we're going to set this up the same way. Take the derivative of your function as it sits. The derivative of y would be 1 times dy dt equals the derivative of x is also 1, but it gets a dx dt term, minus the derivative of x to the fourth is 4x cubed times dx dt. Now from here, what I would go ahead and do is I would substitute in the numbers that they give you to make the algebra a little bit easier. So this would actually end up, and I'm going to drop all the ones off as well. This left-hand side would just become -5. We don't know what dx dt is yet, so I'll leave that alone. Minus 4 times x is 2 cubed times another unknown dx dt term. Well, this would be -5 equals dx dt. Let's see, 2 cubed is 8, and 8 times 4 is 32. So that's minus 32 dx dt. Subtract those from each other. So remember, there's an understood 1 in the front. So 1 minus 32 is -31 dx dt. And then if I divide both sides by -31, those cancel. And we can say that our final result for dx dt is going to be a +5 over 31 because the negatives will cancel each other. So no word problem just yet, but this kind of shows you how you have to pay attention that every derivative gets an implicit term, and then we can evaluate it based on the numbers given. Let's do another one just like that. So what about number 2? If I give you that y is equal to 3 times the square root of x, I would like you to find dy dt when x is equal to 9 and dx dt is equal to -4. Now this time, before I go and take some derivatives, I notice that there's a square root in my original function. So I'm going to rewrite that so that I can take the derivative of it on the next step. So we've seen a number of square roots in this class. By now, we should be comfortable saying that the square root of x is equal to x to the 1/2. Take the derivative of this implicitly. The derivative of y is 1 times my implicit term, which is dy dt, equals, doing the power rule here, that would be 3/2 x to the negative 1/2 times dx dt. Now, before I start plugging numbers into this, it might help us to clean up, especially that right-hand side a little bit. So this would just be dy dt, because I'll drop the 1 off. I'll move the negative exponent to the bottom and make this 3 over 2x to the 1/2 power, still times the dx dt term. And then remember, this would be dy dt equals 3 over 2. And once again, x to the 1/2 you can now put back as a square root function and make it easier to evaluate. Now we're trying to solve for dy dt here, which is already by itself. So the only thing I have to do is to plug in my x and my dx dt term into what I have. So this would be dy dt is equal to 3 over 2 times the square root of 9 times dx dt, which is -4. All right, let's see. 3 times -4 is going to be -12 on top. On the bottom, I know the square root of 9 is 3, and 2 times 3 would be 6. And then -12 divided by 6 is -2. So that would be your dy dt value of this implicit derivative based on these values. Oops, sorry, too far. Hit the button too hard. So the next couple I want to do, we're going to move into some e's and logarithms as well. So number 3, if I tell you that y is e to the 2x plus 1, can you find dy dt when x is 4 and dx dt is 0.5? Well, this one I don't have to rearrange. I can take the derivative implicitly as it sits. So we've done the derivative of y a few times now. That's just going to end up being dy dt because the 1's going to go away. Remember, when you take the derivative of an exponential function, you take the derivative of the exponent, which is 2x plus 1, and bring that to the front. You leave the e alone, but in this section, we have to add the dx dt term on. Now I can plug my x equals 4 and my dx dt term in, and we can say that dy dt is equal to 2 times e to the 2 times 4 plus 1 times dx dt, which is 0.5. Now in this case, I actually notice here that 2 times 0.5 is just going to be 1. So those actually end up going away because you don't have to write the 1 down. And then if you simplify the power of e, 2 times 4 is 8, and 8 plus 1 is 9. So that becomes e to the 9th power. So if they want the exact answer, that is what you would type in. If they want an approximate answer, so you can go to your calculator, ooh, this is a big number. This would be 8,103.083. Just make sure you read the instructions on your homework or quiz and see which answer they prefer in this case. All right, and then one more warm-up one. I know we did 4 of these, but it's good practice of a natural log function. We haven't done a lot of natural log derivatives recently. If y is equal to the natural log of x squared minus 2x, find dx dt when x is 5 and dy dt is 3. So first thing I'm going to do is take the derivative of this implicitly. So in this case, the derivative of y, once again, is just going to be dy dt is equal to, remember, when you take the derivative of a natural log function, whatever is inside the natural log, that goes on the bottom. You take the derivative of that and you put it on top, which would be 2x minus 2, and then don't forget to multiply this by dx dt. From here, I can plug my x and my dy dt values in and simplify to solve for dx dt? Well, dy dt is 3. This is equal to 2 times 5 minus 2 over 5 squared minus 2 times 5 times dx dt. This would be 3 equals, let's see, that's 10 minus 2, which is 8. This is 25 minus 10, which is 15, times dx dt. And if you're trying to get the dx dt by itself, you need to get rid of that 8/15. So I would multiply both sides of the equation by 15/8. Because on the right-hand side, the 8/15 and the 15/8 would cancel to give you just the dx dt. And on the left, 15 times 3 is 45. So your value just becomes 45 divided by 8. So there are 4 good examples of how you can take implicit derivatives and evaluate them at whatever values are provided. Now that we have this idea down, what I'm going to end this section and actually end this class on is we're going to do a few word problems that have to do with these rates of change of everything to end. So let's look at number 5. I want you to find the rates of change of total revenue, cost, and profit with respect to time. Assume that R of X and C of X are in dollars. So if I tell you the revenue function is 280x minus 0.4x squared, and I tell you the cost function is 5,000 plus 0.6x squared. Now looking up at the top, it's talking about revenue, cost, and profit. I didn't give you a profit function here, so the first thing I'm going to actually do is I'm going to find my profit function. So P of X, remember, has a formula of revenue minus cost. If I plug these values in, this would be 280x minus 0.4x squared minus my cost function, which is 5,000 plus 0.6x squared. Distribute that negative through, and you get 280x minus 0.4x squared minus 5,000 minus 0.6x squared. Putting your terms together, if you put the x squareds together, you're just going to get a negative x squared. You're going to have the plus 280x, and you're going to have the minus 5,000. So while that's not an answer to anything, that is your profit function that we're going to need. So what they want us to do here is they want us to take the derivative of all 3 functions, so revenue, cost, and profit with respect to t, and then they want you to plug the 2 numbers in. They want you to plug in x is 200, and they want you to plug in dx dt is 300. So let's do that. Beginning with revenue. The derivative of r would be dr dt. So the derivative of this would be 280 times dx dt minus 0.8x times dx dt. I'm then going to plug all my numbers in. So this would be 280 times 300 minus 0.8 times 200 times 300, which gives me a rate of, let's see, 280 times 300 minus 0.8 times 200 times 300. That gives me a value of $36,000. So the rate at which your revenue is changing is $36,000 a day. Do the same thing for cost. We're going to find dc dt. So take the derivative of your cost function from the top. Well, 5,000 goes away, and that's going to be 1.2x times dx dt, which if I plug my numbers in, that is 1.2 times x, which is 200, times dx dt, which is 300. And that has a value of $72,000. Now, once again, we did this back, and I think it was section 3.5, and we talked extensively about this in the video, that once you find revenue and cost, when it comes to profit of the same value, you can either plug your number into your derivative of your profit function, or you can just subtract the values. Now, the one thing I will do, even though it's not necessary, is I am going to find dp dt. So I'm going to take the derivative of my profit function, which would be negative 2x times dx dt plus 280 times dx dt. I can plug the same values into this, and you should get the following answer, which would be negative $36,000. Now you'll notice I didn't actually plug them in because, like I mentioned, once you know revenue and cost values, you can use your formula that the revenue function minus the cost value will be the profit value. So I just did in my head 36,000 minus 72,000, and I got negative $36,000. But once again, you can also plug the numbers into this dp dt function, and you'll get the same answer I wrote down. All right, how about number 6? For loose landscaping, the total revenue and the total cost in dollars for yard maintenance of X homes are given by R of X is 1,000X minus X squared, and cost is 3,000 plus 20X. Suppose that Loose is adding 10 homes per day at the moment when their 400th customer is signed. At that moment, what is the rate of change of total profit? So this problem is similar to the one that we just did, except that not all the information is provided explicitly for us. The first thing I see is that it's asking about the rate of change of total profit. Now, once again, I didn't give you a profit function here. So before I dive into the rest of this, let's find our profit function. So P of X is going to once again be your revenue function minus your cost function. This will be 1,000X minus X squared minus the cost, which is 3,000 plus 20X. This would be 1,000X minus X squared minus 3,000 minus 20X. And then I'm going to put my terms together. You should get a negative X squared plus 980X minus 3,000. Now, it also says what's the rate of change of this total profit. So I'm going to take the derivative of this, but remember in this section, we're taking the derivative with respect to t, right? So over here on the right, I'm going to find dp dt. So that would end up being negative 2x times dx dt plus 980 times dx dt, and the derivative of negative 3,000 goes to 0. Now the question is, what numbers are you plugging into this to get your value? Well, let's go back to our problem here and let's do this in green. It says Loose is adding 10 homes per day. And I said green and wrote it in red, my bad. So 10 homes per day. That is a rate at which you're adding. So we can actually say that our dx dt is going to be positive 10 because you are currently adding 10 homes a day. That's not a static number. It keeps going up every day. At this current moment, you have 400 customers that are signed. Now that is only at this moment in time, so we can define X as being 400. I would then take these values and we can plug them into our rate of change of our profit function. So this would end up being -2 times 400 times 10 plus 980 times 10. When I type that into my calculator, give me a second, I get a value of $1,800. So what that means is that at this moment in time, if you have 400 customers and you are adding 10 homes a day, your profit is increasing at $1,800 a day based on this data. So there's a good example of how you can take implicit differentiation and related rates to find a constant rate of change of your profit. All right, and then just one more to wrap up this video. It's the same idea, only I needed to mix one in that had a product rule, so let's do that here. Suppose that the price P in dollars and number of sales X of a mechanical pencil are related by the following equation. 5P plus 4X plus 2PX is equal to 60. If P and X are both functions of time measured in days, find the rate at which X is changing when X is 3, P is 5, and dP dt is 1.5. So first off, when it says find the rate at which X is changing, it's asking you to find dx dt. So keep that in mind. The first thing I'm going to do is take the derivative of this function because I need to get a derivative to do all these rates of changes. So going from left to right, since everything is a variable, you have to add an implicit term onto it. So the derivative of 5p would actually be 5 dp dt. The derivative of 4x would be 4 dx dt. And then, as I mentioned, you've got two terms that are being multiplied together in 2p and x. So if I call 2pf and I call xg, we can do our product rule, which, remember, the product rule is fg prime plus g times f prime. So if I perform the product rule there while also doing implicit differentiation, this would be plus my f function, which is 2p, times the derivative of g, which would be 1 times dx dt, plus my g function, which is x, times the derivative of f, which would be 2 times dp dt. This whole thing is equal, because now I'm done with the product rule, the derivative of 60 is 0. Now you got a bunch of variables floating around here. Before I try to move things around and throw anybody off, why don't we take these three values that they gave us and let's plug them in to everywhere I see in this derivative. So this would end up being 5 times 1.5 plus 4 times, remember, we don't know what dx dt is yet, plus 2 times p, which is 5, times my unknown dx dt, plus x, which is 3 times 2, times dp dt, which is 1.5, is equal to 0. All right, cleaning this up a little bit more, you're going to end up with, looks like 7.5 plus 4 dx dt plus 10 dx dt plus 9 equals 0. All right, I can put a couple of things together here. So I can add the two constants that don't have a dx dt term on them. 7.5 plus 9 is 16.5. Since both of these are dx dt terms, I can add them together and make this 14 dx dt is equal to 0. I'm going to subtract the 16.5 over to make this 14 dx dt equals negative 16.5. And then if I divide both sides by 14, if they're looking for an exact answer, it would be negative 16.5 over 14. Or if they ask you to just put that in your calculator, it would be negative 1.179. Make sure you read your instructions, though, on your homework and quiz to see which answer they prefer. And that is another example of an implicit differentiation to calculate a rate of change. Well, that officially ends section 3.9, and that officially ends the last section of Business Cal. So we have now covered all the sections that are necessary for your upcoming final exam.